Are you all Tuesday lab group? No. Yeah, okay, mostly. Okay, good. We have 6 people in the class. Would have been awkward if nobody showed up. I still have to present because it gets recorded. So it's going to be awkward. All right. So I'll be going on leave pretty soon. So this is my last lecture for this unit. So David will take over from here, from week 9, week 10, and the rest of the lectures and everything. So so if you have questions and things, you can email me. Also, you can check with me this week or next week, right? So now we are at the midpoint of this unit. So I've been sending emails to people. So don't worry if you get an email, or don't worry if you don't get an email. So I'm just checking up with everyone how they're doing and how they're scoring the assignments and the online quizzes and stuff. So this time is quite a good thing. Many people got all the answers correct for the online quiz. Probably it is getting easier, or you're spending more time on it, which is good. But this is what I want to see. And also, the final exam duration is 2 hours. Probably you already have the exam timetable. Did you have a look at the exam timetable? Do you know when your exam is for 376, 676? It's I think it's 10th of November. It's a Monday, 10 a.m. Or is it 10th of November? Yeah. And the exam duration is 2 hours and 10 minutes. In the unit guide, there was a typo. It's written. When is it? 25th November. Is it? 25th? Okay, so it's on 25th November, 10 a.m. So you have plenty of time to prepare, and it's a Monday. So, and I think it's the first exam, 10 a.m. So you will be fresh, and yeah, so it's not in the afternoon, so you won't be sleepy. So it is 2 hours and 10 minutes. So 10 minutes for reading the questions, and then 2 hours for attempting. So it's not 3 hours and 10 minutes. Okay. All right, just checking with the isolation, because we're gonna look a little bit more into isolation today, or isolation and leakage. So isolation, we talked about it, isolation and leakage, 2 pathways. One is from the local oscillator to RF, which we call the LR isolation or LR leakage, and the other pathway is from LO to IF, which is the output, which we call the LI leakage or LI isolation. Okay, so isolation and leakage are 2 opposing terms. We want isolation to reduce leakage. If there is more leakage, we call it less isolation. So we want good isolation. We don't want these ports to interfere with each other. So why particularly LO? Why we don't say RF to IF? Because RF to IF usually is not much leakage, because RF signal is quite weak. The strongest signal is LO signal, which is locally generated. But LO can couple to RF, and RF can couple to IF. In that way, it is really bad. But the original problem starts with LO most of the time. Okay, you know how to test them. So you to test the leakage between LO and RF, you put your source here. You put at the LO frequency in, and you check for that frequency at the RF. Although RF is the input for the entire system, just for this testing purpose, we take it as output and check for this LO frequency that might have coupled to that port. And same with the LO and IF. So we give the LO signal here and measure or detect that particular frequency. What is the strength of that frequency here? So each mixer, a switching mixer, we can implement a switching mixer using a MOSFET or a BJT. And when you use a MOSFET or a BJT, you have these significant capacitances on between the gate and the source, and also gate and the drain, as we have seen before. So we checked at the parasitic capacitors, the performance, how it affects at high frequency. And you have done a lab on that, and you know at higher frequencies the performance goes down, the leakage goes high. And in these communication systems, we are talking about hundreds of kilohertz or even megahertz, and sometimes gigahertz. So this isolation is really an issue when we go for really high frequencies. So let's look at this problem. So this is a switching mixer with a single MOSFET, and we know there is this gate to source parasitic capacitance there, which is 1 picofarad given there. Your RS is 50 ohms and RL is 10 kilo ohm. So you're operating the local oscillator frequency at 10 megahertz. So what is the coupling, or what is the leakage of the local oscillator signal to this point X? How do you find that out? Anyone? Yeah. So I'll repeat what you just said. The capacitor provides a pathway for the signal to reach from the LO side to X, right? And depending on the frequency, the capacitor offers different amount of impedance. So this is like an impedance here because of the capacitor, and a resistance here which goes to the ground. So this is basically a voltage divider. Can I say it's a voltage divider? So this divides the voltage by the ratio RS divided by RS plus the impedance of the capacitor. Okay, can you see that? So that is the VLO there, and then you have this impedance ZC, then you have this resistance RS which goes to ground through VRF, and here is your point X. So VLO is divided as this voltage and this voltage, and the ratio that comes at X, which is the point X to ground, is RS divided by RS plus the impedance of the capacitance, which is what? 50 divided by 50 plus. What is the impedance of the capacitor? One divided by SC, which is same as 1 divided by S is J omega. Omega is 2 pi F. F is the frequency, which is 10 megahertz, times C. C is 1 picofarad. What is a pico? 10 power minus, what is pico? 12. Yeah, 10, yes, 10 power, 10 times 10 power 6. Yeah, 60 kilo. Can you say that, so this is the 1 divided by number? So 1 by J times, after inverse, that's 15.9, 10 power or 1.59, 10 power 6. So what do you get? So ZC is 1 divided by J 2 pi 10 times 10 power 6 times 1 times 10 power minus 12. One over J, right? So when you find the inverse, the J become negative, right? So that is negative J. What is the inverse of this? 1 by 6.28 times 10 power 5. Okay. So if you don't have a complex number calculation in your calculator, you can find the absolute value here, which is 50 square plus, or square root of 50 square plus this square, the whole root of that. Okay. Then you will see what would be the fraction of the VLO that goes to the point X. So what is the answer? What do you get? What? Anyone? Does it come in 10 power minus 3? Yeah, 3.1 times 10 power minus 3. So if VLO was a unit of 1, 3 milli unit goes into the point X, right? Any questions how we got that number, or how to do this? Yeah. With the
slide for this week lecture. You can see it on.
oh, it's not uploaded.
Yeah.
Oh, okay. It should have come now. By now, I've done it like. So I'll do it right after this. Give me a moment. So by that time, try to do the question if the capacitor was on the other side between gate and the drain. How do you solve that problem? We'll come back to that soon. Okay, if you refresh your pages, you will have access to this document now. Have you got it? All right. Okay. So, as I said, so now we will look at the capacitor on the other side, the capacitor, a parasitic capacitance between the gate and the drain. So how do you tackle this issue? So the question is, again, find the leakage or find the fraction of voltage at the point X. So now you need to remember what you learned before for the high frequency operation of MOSFETs. So anyone, how we start with this problem? How are we going to tackle this? Do you remember we had in our small signal analysis, we had this capacitor here, which we represented as C mu, and we brought it into this side as C equivalent, right? Do you remember that? So C equivalent, how did we do that? It was 1 plus GM RL times C mu, right? So there was a derivation also. We looked at the derivation as well before. So how, when we have a bridging capacitor like that, we can bring it to the input side and use it as the equivalent capacitor. And if we had the C pi capacitor there as well, the total capacitance, the input capacitance will be C pi plus C equivalent. So that's the same case here. So this is our gate, this is the drain, and this is the source. The same thing happened here. There is a capacitance, the capacitor is C mu, and that is between the gate and the drain. So in order to find what is at X, you bring it to this side as C equivalent. And how do you find C equivalent? You can use this. So the capacitor value you are given, 1 picofarad, is the C mu. You are given GM, RL is given. Now you can find the equivalent capacitor between the gate and the point X, or the gate and source. And the same as before, you use the voltage division to find the component voltage fraction at the point X. How much do you get this time? What is C equivalent? So GM is 30 milliamps per volt, RL is 10 kilo ohm. So GM RL is so one is milli and another one is in kilo, they get cancelled, so it's 300 is the GMRL. So 1 plus GMRL is 301. 1 plus GMRL C mu is 301 times 1 picofarad, which is 301 picofarad. Right. What is it? Vx. Is it 0.09 or 0.9? This is a 10 megahertz, right? Closer to 0.9. Oh, 0.5. Okay. This is the simplest problem that one can ask.
0.9?
Is it?
0.99.
Is it 0.99? We got to answer 0.99 and then 0.5. 0.69. So the division would be again the X voltage at X would be VLO, the voltage division RS divided by RS plus 1 by SC equivalent. Okay, and S is J 2 pi 10 megahertz times C equivalent is 301 picofarad and RS is 50, same as before. So I let you find out the answer. Okay, 0.69 seems to be right. So why we looked at this is we looking at the classes of different mixers. The leakage is a major deciding factor. So let us look at three classes of mixers called unbalanced mixers, single balanced mixers, and double balanced mixers. Okay, so let's look at the mixing as a mixing using a switching circuit. So we covered this section where we looked at it how a switching waveform can do effective mixing, and you had done it in the lab. Some people on Tuesday's lab have already done that using a switching on and off at a very high frequency. You can mix the RF frequency with a local oscillator frequency, right? So the switch is turning on and off at the frequency of the local oscillator, and VRF is the signal passing through that switch. And at the output side, you get the mixed signal. One of them is the difference frequencies, RF minus LO. But there is an issue here, is when the switch is off, there is no output. And when the switch is on, you get RF. So that means you are effectively not using half of the signal. So VRF is weak anyway because that comes from an antenna, from a distant transmitter. The signal comes in, we capture it with an antenna. So that signal is quite weak. And on top of that, you are using only half of the signal, right? So the conversion gain, the voltage component at the IF versus the voltage component in the RF, it's quite small. It's already half just by using this switch, because half of the time it is open. So how can we improve this? And there is another issue, is there is a strong leakage between the LO and RF. Okay, that's an issue. So we found that we have problems with a capacitor between the gate and the input, and also this one. Okay, one question: which capacitor is the worst? So is it C pi or C mu, which can create the most problem in our mixer? Let us say both are 1 picofarad. Which one affects the mixer most, the worst? It's this one, right? So just the two problems you did. So in the first one, so you were looking at the C pi, and you got 0.0628. What's that? Yeah, 3 millivolt fraction to that. And when you use the same capacitance, 1 picofarad, when it goes to the C mu position, you get 0.69. So it's quite quite a deterioration, we say. So the effect of having C mu is more than that of C pi. So there is, in this case, we have both C pi and C mu. So how do we solve this issue? Any ideas? Its answer is in the next slide, but I would like you to think, how would you solve this if you are posed with this problem? You have the slides, right?
Increase the
you can't increase the capacitance. So increased capacitance actually is making it worse.
Decrease the resistance.
Decrease the resistance, that is the load resistance, and so here there is no resistance, it's zero. We are assuming it's zero. You can't reduce the frequency of RF.
I mean, of LO.
LO, you can't, because IF, you want IF to be fixed. So you need to keep the LO to be fixed. So what else? What do you do? Right, so if you can repeat the same circuit with one more switch, when this switch is open, the other switch closes, right? And then the other switch opens, this switch closes, and couple them to the output, just like you learned the differential amplifiers, right? So if you get the differential output, you solve that problem. So that's what happens here. Because VLO is a switching signal, it is a square wave. So when the positive part of the square wave goes to LO, the negative part, which is VLO bar or VLO complement, whichever way you call it, that goes to the next switch. So when this switch is on, let's say switch A is on, switch B is off. So let us see, does it solve the problem? So we are taking the output V is equal to V out 1 minus V out 2, because that is the differential signal between this point and this point, right? So when A is on, or A is closed, so you get the difference between the two, A minus B, VA minus VB, or you get VRF minus 0. And when A is open and B is closed, which is the second situation, you again look for VA minus VB, which is 0 minus negative VRF, which is positive VRF. So in both cases, you are getting VRF on the other side. Okay, so you maximize the signal usage. And another advantage here is the leakage between the LO and RF is eliminated. How is that? So we have LO signal here, but at the same time we have LO bar signal there, which is the direct opposite sign. So let us say it is a 1 volt here. And what will be LO bar? Minus 1 volt. And some fraction of it leaks to this point X. Remember from that question. Some portion, let us say portion X of 1 goes in there. And at the same time, because the circuit is symmetrical, the same fraction minus X of 1 goes in there. And now to the same point here. So the minus and plus get cancelled. So it's just like your virtual ground in the differential amplifier, right? So the leakage between LO and RF gets eliminated. So that's the good thing. But also there is a bad thing happening here. So the bad thing is the leakage due to this capacitor actually doubles in this case. The C mu capacitor. How is that? Our output voltage is V1 minus V2 across these two, V out 1 minus V out 2. So the fraction of the voltage from VLO that reaches this point, V1, is the portion of VLO, let's call that fraction Y, y times VLO, and the fraction of this voltage reaching at this point is the fraction of minus VLO. It is same fraction, y. So y times negative VLO. Oh. Right, start again. So this V1 and V2, our output voltage is V1 minus V2. So the leakage happening at this point 1 due to VLO, so let's say at the fraction y, that is y times VLO, and the similar leakage at the point 2 is negative VLO times y. So the differential output is the first V1 minus V2. So the total leakage is 2 times y VLO. So you actually doubled the leakage between the LO and the IF. Yeah, which is really bad because now you know the CMU capacitors are the worst. Right? Any questions there? Because next circuit is even more complex than this. Huh?
So it can we connect V1 and V2 together like VRF?
Oh, we want the differential output. So if you connect them together, and you also reduce the signal, your signal is 0. So here we made it because the RF is coming from outside, and the common mode, whatever is in the common mode, is just the noise, right? So remember the common mode rejection in the differential amplifiers. But here we are looking at the differential output, and if you connect them together, your output is always 0. No noise, no signal. Y is the fraction, or you found the fraction of leakage in the question, right? So y, I just assumed a variable there to talk about a fraction. So it was in the problem that we did, it was 0.69 was the fraction. So y was 0.69 of VLO. So I'm just taking a general term as y. So why we reduce the leakage is if you have the leakage that couples the LO to the signal IF, so the signal quality gets really bad. So how do we do it is by repeating the same circuit once again. Yeah, so this is how we do that. So the method you suggested is correct, by not just by shorting the V1 and V2, but taking another V1 and V2 and shorting them together. So you have the circuit that you saw before here, and it is repeated here. And you, same as taking VLO and VLO bar, you take now VRF and VRF bar. So when VRF is 1, VRF bar is -1. So how does it eliminate the LI leakage? So here, let us look at the capacitor, this one. You have this capacitor here, and you have this capacitor here. So when this point gets the fraction of VLO, this point gets the fraction of negative VLO. And the same as before, the two opposing voltages get cancelled. So my question is, can you draw this circuit without looking anywhere? If it is just with switches, like that. So can you draw an unbalanced mixer? So your VRF is coming, VLO is controlling the switch, and your VIF is the output. Is easy? How about single balanced? Yeah, same, repeat it. Now this is controlled by VLO bar, which is important. And this is your V1 and V2. You're taking differential output and you combine the RF input at the input side to eliminate the leakage. And double balanced mixer, you repeat the single balanced. So this is your VRF as before, this is VRF bar, and this is VLO controlling this, and VLO bar controlling this switch, and VLO controlling the other two switches. And now you need to alternatively connect those. So you need to connect the VLO leakage to the VLO side and connect the VLO bar leakage to the VLO. So your output is from here. Yeah? Everything has to be matched. If it's not matched, then it would not work. Just like in a differential amplifier. So in order to eliminate the plus minus together when it comes to a single point, you need to have all the components matched. Yeah, so if you can draw it without looking, that means you have understood the concept of double balancing the mixer. So what are the disadvantages of the double balance? Yeah, that's the disadvantage. Too many components and more chances of failure, because any one component failing means the whole mixer fails. Right? Yeah, cost, more components means more cost as well. So those are the things to remember here. So mostly the same thing. So single balance mixers, simpler circuit, and Li leakage was still there. And in double balanced, the circuit complexity are more, but much better isolation both at the input side as well as the output side. And we make use of the full signal as well. The RF is completely utilized. Right? It is same as like using a rectifier, using a single diode, and also using a bridge rectifier. So in the bridge rectifier, your efficiency is more, converting AC to DC, your efficiency is more. But if you just use a single diode to convert from AC to DC, you're using only half of the sine wave, right? So you have learned that before in some other units. Yeah, same things. So this is the problem I solved in the last lecture before the break. So I just included in case anybody want to look at that again. So what kind of a mixer is this one? Is it a single balanced, unbalanced, double balanced? What is it? The mixer you see in this picture. You sure? You're right. It is a single balanced mixer. Just was testing how confident you are. So you must have seen the same question in the previous year's question paper. Try to find the various frequency components in there. So this is the question. So how do you find out? So it is shown that the VLO is a square wave, and you have the expansion for the square wave, which is here. And now you apply the RF signal into that. What happens? It gets multiplied. Okay, so the output is the square wave, ST, times I bias plus the VRF signal. And if you use the first three terms of the square wave and then multiply with I bias, it's simple mathematics. Multiply each terms within the bracket, and then one of the signal is a mixed signal, and the others there are some harmonic signals, and there are the intermodulated signals. Right. Diksha, you're looking very sad. Why? Okay. Is it the mixer that making you cry? I tell you, this is maybe the easiest part in this unit, mixers, but mixers are really complex. It's a really big topic, and it can go into really deep with complex maths problems. But we are just skimming the surface because otherwise it is too much. But the other MOSFETs and transistors, they are relatively simple. But as far as this unit is concerned, there are only a few ways I can ask the questions with this limited learning material that we have. Right. So in terms of the unit, it's easy. Now, once you know the concept, why you do what you do, it's easy. So this one, maybe we're going to the last part, looking at passive and active mixers. So if you just have a simple diode or simple MOSFET working as a switch, you're actually just like this before. You are just transmitting the RF to the output only. We are not actively amplifying the signals. So these are passive filters, but there are something called active filters, where you actively amplify the signal at the same time when you mix. So three essential parts of a active mixer is the voltage to current converter, a current switch which switches mixer, and then a current to voltage converter. Right? So we use a voltage to current converter because here we are using the current modulation. Okay? So we are biasing it the current, and we are changing the current bias. That's why we require a voltage to current converter. Okay, remember the differential amplifiers with the current source at the bottom of the common point. So here we are modulating the current source by an external voltage. So we need something to convert that external voltage into a current. So that's here, V to I converter. And then you need the switching action, the two face-to-face MOSFETs for switching with LO and LO bar. So that is the current switch. And then once you switch it and once you mix it, you get the output in terms of voltage. But internal to the circuit, the modulation is in current. So in order to convert the current to voltage, you need a current to voltage converter, which is just these resistors. Okay, so those are three parts. You can see the same parts in the lab when you do the lab. So this is the simplest way of configuring this mixer, right? The same thing now with switches instead of MOSFETs, but again here we are looking at the current, not voltage. So if you the RF that you pick up from an antenna, it's a voltage, so you need to convert it to a current. So any questions on that? So we are not going too much in depth into active and passive filters, which I want you to know about this. And also, this is not, what I'm going to tell is not for any assessment, just so that you know. Now that we have learned the hardware of mixers and we do the lab, there is something called software-defined radio. Have you heard about it? So software-defined radio is converting all these hardware into software. So we do mixing using software, using FPGA programming. Right. So then you ask, okay, then why am I learning this mixer? So the thing is, if you don't know this mixer, you don't know SDR. So SDR is the next step. And SDR means software defined radio. That is, it's not a new technology. It's been around for more than 10 years, but it is getting more and more popular now with a lot of communication channels shifting to SDRs. So in that, all mixing, everything is done using software, or we call the software language for hardware, which is the VSDL software. So, but you need to know these principles in order to work in software-defined radio, right? In software-defined radio, you do amplification, filtering, mixing, everything using software. So the good thing of that is you need to have just one platform, which is a chip, say a FPGA chip. So you can change amplification. You can have different systems implemented on that chip just by changing the software. You don't need to implement a new hardware. So producing new devices is really easy and quick because you're just changing the software. Yeah, so there are some professors doing SDR here in Macquarie. Who is that? Sam Rumsfeld, and probably Raheel, or Idis Setin. Yeah. Any other questions? So what you have learned in the nonlinearity and mixers part in the last 3 weeks is, so we looked at the response of a nonlinear system. So before that we were saying that, okay, we assume that all devices are linear. We were eliminating all the higher terms and then looking at the small signal model. A small signal model is essentially we are looking at only the linear part. Even though it is not linear, if you zoom in properly, just for our purpose, we assumed it is linear. But when we came to the nonlinearity, we definitely looked at the nonlinear part of this response. So we looked at harmonics, modulation, intermodulation, and fractional harmonic distortion, total harmonic distortion, and all. And then we looked at the nonlinearities of diodes, BJTs, and MOSFETs. Okay. Then we looked at the mixer basics and its performance parameters like voltage conversion gain, power conversion gain, noise figure, signal to noise ratio, and then implementing the mixers with MOSFETs and BJTs. Today we looked at leakages and isolation again, looked at the 3 classes of mixers, unbalanced and 2 balanced mixers, and just touched on active and passive filters. So I will be uploading more practice questions on iLearn on the nonlinearity and mixer part. And I will be on leave soon. I don't know exactly when, but from the week after next onwards, probably for a few weeks. So if you have questions, you can send me email or wait for me to come back. I should be back. I should be back before, 21st November. Yeah, and assignment 3 will be on today or early tomorrow morning. But I see that you get less than 2 weeks, strictly speaking. So I'm going to extend the deadline to 3 more days, so you get 14 days exactly. But it's not that it makes any difference. I see everybody start doing in just the last 2 days. So even if I give you 6 months, it makes no difference. So you will see David Moore now. He'll be taking the lectures on week 9, 10, and 11 on power amplifiers. And it's time for some feedback, if you care. What is it?
Even lower than struggling. Because this one is really complicated, and when we go to that, it's more.
Oh, I thought the lab, this one is easier, isn't it? Who did the 2-stage labs?
No, I didn't want to choose the other one.
Easy, right?
Yeah, it was easy. But the difference was terrible. You get loud? Loud. Yeah. The last slightly terrible, the differential amplifier.
Yeah, so we're just trying to balance it. We got feedback that the differential amplifier lab was a little bit too tough.
In differential gain, and for testing a single engine, it's somehow it's
Totally the
yeah,
same because
especially the with the active load. It's showing it has very large error in simulation and in real life.
Right.
we can show is this the right answer or not. Because it's a bit different. Even when DC is correct.
Yeah, the gain gives.
Sometimes you run a simulation it is even wrong.
Oh.
Yeah. Two people, two different. And this two different results. You would copy paste.
So it can't be wrong in 2 same circuits in 2 different computers. It may be something to do with the files you have included, the BJT files you included.
It's actually the file with the PNB, BJT, so it's already in these files.
Okay. So no one very confident.
You can do it.
So I see more people struggling than people say somewhat okay. So what can we do to bring more people from struggling to somewhat okay and more people from somewhat okay to very confident?
One more course.
Free course.
This is free course and there is consultants. You are always welcome to come and meet us and discuss like for 1 hour or more as much as you want.
Another course next moment.
So what is so you said you're struggling here, I see. So what is causing it? What can make it better? So now we have a problem. Now we need to find a solution. What is that?
Can we have a tutorial on how to make a lab report?
So in iLearn, you will see that there is a template file, which also has all the instructions. So it looks like a template file, but the contents of the template files actually, if you look at the fonts in red, they are the instructions what you should include in the report, right? So work with the theory. So you have theory background from the lectures, and you have lecture notes, and then you have your results, and you have come across problems, and you try to analyze why it caused the problem. So if you can't analyze, then there is no point, right? So as an engineer, you don't always get what you want. So you try to build a circuit, you get something really bad. But the value comes in when you find out what went wrong and correcting it next time. So in this case, we don't have a next time, but at least you go half the way to find out what went wrong. So only when you know what went wrong can you make it right next time. So as Einstein defined, someone asked what is insanity to Einstein, and Einstein said, doing the same thing again and again and expecting different results. That is insanity. So don't be like that. So try to find out what went wrong and correct it. So we are learning those engineering skills in this unit. So that's why I would say, so if you didn't get the results, you need to say why you did not get the result. And okay, here I want some suggestions from you. So if you can suggest, more suggestions are welcome, but if you can suggest like one thing you want to get implemented in this unit or in this topic of mixers, please do write. Oh, you can write. You'll see your comments captured and recorded, and it'll be there forever.
One question about that report. Do we have to capture the waveform in the simulation? Because the waveform is pretty small, and when we put it in the lab report, we can see it.
It's really thin.
Then
Really thin. And when we put it in the box, it's just black or white.
okay. I think you can make the figure small. So if the window, you drag it to make the window smaller, not a big window, and then you screen capture it. It's thicker actually that way. Can you write equations more clearly and mark up some sign meanings? So submission work, is it assignments? See, last year there were 4 lab reports for 4 labs. This year it's half. Yeah, only 2. And yeah, yeah. So you have 2 labs. So yeah, have you been checking the weekly schedule? So you see. More pre-lecture videos, yeah. So you're writing only 2 lab reports. Do you know how many I have to go through? 85 times 2. Or David will go through 85 and I will go through 85. So what is good, 1 or 85? Yeah. Many people have clashes with their other classes, so they're all relying on the captured video. Okay, any more? Oh. I can't cancel when it happens. Okay, thank you everyone. It's been such a pleasure to teach you. I hope you learned something. And I'll see you. Yeah.
How can I get the access to the lab? Like, I need to stay in the lab for days. So.
You need to stay in the lab whole day. Which lab?
We did it 2 days ago. Only file. Yeah, because we only got the wrong result. So in the
You have to stay in the lab only. So how can I get the access to the room?
Oh, access to the room. Oh, I don't think even I have access to that room after hours. But there are some people working in the other labs, right? 239 or something.
After 5 every lab.
Yeah. Okay. Yeah. Somebody said more boosts last time as well, so you need some professional help. That is true. I don't know who that is, but all right. So I'm going to lock it. If there is there anyone entering more? Okay, all your comments are well taken, except for more booze. Can't do anything about that. Thank you very much. You've been a wonderful, wonderful class, and all the best for the exam, which is 2 hours 10 minutes.
How many questions?
We haven't decided yet, so it'll be similar format as last year. So there are question papers available in the library. I don't know, are you aware of that? You have all the previous years. So the format won't be very different. So in order to make sure that you understand, we also have the mini exam, which is in week 11. Right? No, so there is a mini exam, which is like carries 5% of the marks. It's no big weightage, but this will be easy. And it'll prepare you for the final exam as well. So the format will be same, but the number of questions may be different. and probably the formula sheet will be the same.
How long will the meeting take?
I think it is 40 minutes or 1 hour, 40 minutes, I think.
But would happen like in the last 40 minutes or in the first 40 minutes? Because we have a engineer treatment before this, so if my class would be at the beginning of this class.
Okay. I think it will be last 40 minutes. Yeah. Okay, thank you. Save.
Sorry, I still didn't understand the words.
Turn that.